All right, here we go.
You're the one talking about it.
Here, you're going to need your own paper. Please get out a sheet of paper because I did not leave space on here.
I get some legal pad paper. I get some.
What the answer's like?
It's like 44 ounces.
All right, everybody got a review sheet? All right, everybody. Everybody's locked in here, paying attention. And we are ready to go. So, number one, I have 4 boys and 6 girls. I'm going to pick 4 ABC. I'm picking 4 and asking a probability. So for A and B and C, the denominator will be 10C4. Why is the denominator of all of these problems 10C4?
You're choosing 4 students.
Because there are 10 kids to pick from, and 4, I'm picking 4. It's like a card problem, and there are 52 cards and you're picking 5. In all of these problems, there are 10 kids and I'm picking 4. Now, what do I want? What is the probability that I'll get exactly 1 boy? Well, I'm going to get exactly 1 boy. Isn't that 4C1? But I also have to get then 3 girls. Because if I am picking exactly 1 boy, doesn't that mean I have to have 3 girls? Because I'm picking 4 kids? Can I get a nod?
Yes.
I'm picking 4 kids. 1 boy and 3 girls. So 1 from the boy pile, 3 from the girl pile. And that's the answer to your question. So whatever that is. Looks like about 0.38. 1. I round out to the nearest thousand. 0.381. B. What is the probability that I'll get at least 1 boy? Now let's think about that for a minute. I'm picking 4 kids, and I want at least 1 boy. So doesn't that mean I need 1 boy, or 2 boys, or 3 boys, or all 4 boys? Isn't that what that means? Now, I've already done this one. That is 1 boy right there. Could I do a similar thing for 2 boys, and 3 and 4? And then I would add all those up, or, I would add them all up. We talked about this before though. Instead of looking at what you want, sometimes it's easier to do 1 minus what you don't want. So what do I not want? What is the only thing I don't want?
0 boys.
0 boys. So what if I did 1 minus 0 boys? So that would be, I gotta be careful here. That would 66, or no, 64 over my 10C4. So here's the probability of no, or maybe a better way is to say all girls. Here's the probability of all girls. No boys at all. So if I take 100% or 1 decimally minus all girls, would that leave me with all this up here? So here we go, what is that? Wow. I got 0.929, basically. Anybody else get that?
Yeah.
So there's almost a 93% chance that given this situation, I'll get at least one boy. At least one boy. If I choose 4 students, what's the probability I'll get more girls than boys? Well, what does that mean? If I have to have more girls than boys, that means I need
3 girls.
I need 3 girls, so 6C3, and 1 boy. Or what else?
4 girls.
4 girls. So 6C4. So this is 3 girls and 1 boy. This is 4 girls. And if you want, sometimes people stick this in. That just says no boys. You don't need to put that in, but if that makes it more balanced to you, you can. And that's it. I just need to get 3 or 4 girls. And I got 0.452. Did you? All right, let's look at number 2. What is going on there? What do you think? What should we do? Like a tree, very good, Cindy. So what's my tree gonna look like? Well, what are my things here? We have math and we do our homework. I wanna know the probability of doing homework. So first I'll work on math or no math. You know, next year, math every other day. Oh my goodness. It is terrifying. All right, so you don't have to set up a tree diagram. I find it easiest personally, organized. There's a lot of numbers going on here. I find it easier to organize it this way. Ultimately, we need to find this probability and this probability. We want him to do his homework. What's the probability he does his homework? So, the probability he'll have math tomorrow is 80%. So the probability of math, I'm not making it up, it says it right in the problem. The probability of math is 0.8, which means the probability of not math is 0.2. Now, if he has math, there's an 87% chance he'll do his homework, which means there's a 13% chance he won't. If he doesn't have math, there's a 31% chance, which means there's a 69% chance he won't. Do All of those numbers look okay to you. So now we're gonna multiply these two. Right here, we're gonna multiply those. We're gonna multiply these. And then we are going to add those two answers. Does anyone have a question? I see a couple of stares out there. Anybody have a question about where one of my numbers came from? I got 758 as my final answer. Are we okay?
Yes.
Besides Sydney, who recognized that a tree diagram would be a good way to approach that problem? Did y'all recognize that? Because tomorrow, I'm not telling you how to do the problem, it's just gonna be there. All right, number 3, what's the probability of drawing both the king and queen of spades if you draw 4 cards from a standard deck? What's your denominator? This is a probability question. Denominator is 52C4. We got 52 cards, we're gonna pick 4. Now, what do we want? We want the king of spades. How many kings of spades are there in the deck? There's 1, right? And I want him. There's only 1 king of spades, and I'm getting it. If I wanted a king, that would be 4C1, right? Because there's 4 kings. There's only 1 king of spades. I'm getting it. What about queen of spades? There's only 1, and I'm getting her too. Here comes the tricky part, the forgotten part. How many cards are in my hand? 4. How many do I have? 2. I need 2 more. Where are they coming from? Anywhere else? No, not 52. 50. C2. Yep. Why 50? Because I already took the king and queen of spades out. And I can handle any of the other cards. Did you get .0045? Find the probability of rolling exactly 2 4s in 6 rolls of a die. Okay, now, I'm gonna do this experiment 6 times. No, yeah, 6 times. And I wanna get 4 exactly twice. So of my 6 rolls, I need 2 of them to be good. Give me what I want. Do I care which 2? No, that's why there's a C there, because I don't care if it's the first one, the second one, the 5th one, doesn't matter. I just gotta have 2 of those be what I want. Now what I want is a 4. What is the probability that if I roll a die, I'll get a 4? 1 out of 6. And I want 2 of those. I want 2 4s. What's the probability I won't get 4? 5, 6. And since I'm rolling the die 6 times, I gotta have 4 of those. What? No, this is exactly, yeah, certainly if I did the experiment, I could get 1. I want, what's the probability of exactly 2? this gives me the probability.
Oh, it does say exactly.
Exactly two. So 62 times 1/6
I don't.
squared times 5/6. I got just about exactly 0.201 basically. Now, number 5, I have a typo in there, but it is basically the same kind of problem. If I have 10 questions, and there are 5 options for each question, would you agree that the probability of my guessing right is 1/5?
Yeah.
So my correct probability is 1/5, and my incorrect probability is 4/5. So when I say these two problems are alike, they're basically the same thing. Here I'm rolling a die, and either I'm gonna get what I want, or I'm not gonna get what I want. Here I'm gonna get it right, or I'm not gonna get it right. Now, what is the probability of guessing more than one right on a 10-question quiz? Guys, that's overwhelming. What does that mean? More than one right means I either get 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. So I would have 8 of these to do. No, we're not doing that. What do I not want? One right or 0 right. So what if I took 1 minus the probability of 1 correct and minus the probability of none correct? So 1 is, that's everything. If I take out what I want, which is 2, 3, 4, 5, 6, 10, then that's gonna leave me, that's what I want. This is what I don't want. So what will this look like? 1 correct. 10C1, 10 questions, 1 correct, 1/5 to the first, 4/5 to the 9th, 10 questions. 1 of them right means 9 of them wrong. And then I also have to subtract none correct, which would be 10C0, 1/5 to the 0, and 4/5 to the 10th. So this is 1 right, 9 wrong, and this is none right, 10 wrong. And that will be my answer. I got 0.624, but I'm not gonna swear by that.
That's what I got.
Perfect. Some of you look really, really bored. If you don't wanna review, that's fine, we'll start 9/4, but we have a quiz tomorrow, when I see you, we're gonna get the quiz. So, you wanna stick with the review?
Yeah.
All right, let's keep those eyes open. Here we go, number 6. Jar 1 contains 3 red and 5 blue. Jar 2 contains 6 red and 2 blue. Find the probability of drawing a red ball if 1 ball is chosen. dilemma. Are all the balls in the same basket? No. So if I'm doing this experiment, there's 2 baskets. And the first decision I have to make is, which basket am I choosing from? So I walk into the room and I'm either taking it out of basket 1 or basket 2. And the probability of each is 0.5, right? I mean, if they're just sitting there, 50,
So this
half
is the
chance
tree.
here, half chance here. Now, if I take it out of jar 1, it can be red or blue. Is the probability of being red 3/8 in jar 1? And blue would be 5/8? Would you agree with that? And then what about jar 2? Again, we can be red or blue. That would be 6/8 and 2/8. And I want the probability of red. So I get 1/2 times 3/8, or I get 1/2 times 6/8. So that's 3/16 and 6/16. So the answer is 9/16. Now, because I only picked 1 ball, I think some of you are saying, well, wait a minute. I have how many red balls altogether?
9.
I have 9. How many balls altogether do I have? All balls together? 16? Oh, no. Aren't there 16? So the probability of getting a red one is 9/16. That falls apart if you're taking more than 1 ball. Alright, so as long as I'm just taking 1 ball, you can do it that way. But not if you're taking more. Alright, A and B are events in sample space S. We did this yesterday. How did we do these yesterday? We did them with a Venn diagram, remember?
Yeah. And it was like 3.
So let's see if we can put these numbers in our Venn diagram. So we have, so apples and bananas. We know that the probability of apples is 0.74. The probability of bananas is 0.42. And the probability of both, which yesterday I actually used a symbol, here it says and, that means both, is 0.32. So that goes right here.
So we just subtract that.
And then we can figure out what this part is. That would be 0.42. And we can figure out what this part is, 0.10. Now, what does the first question mean? What does this mean? Not A and B. So in other words, only B.
Yes.
So that would be 0.10. The second one says, not A or B. So that's the folks that are out here. We don't know that, but we can figure it out. Because these all have to add up to what? 100. 1. And if they don't add up to 1, then the leftovers are out here. So don't these add up to 0.84? Which means 0.16. So the answer to B, the people who don't like either one, not A, not B, that's 0.16. And then 7 says the probability of A given B. And I gave you a formula for that yesterday. Do you remember what it is? probability of both
Over.
over the probability of just B, the total probability of B. So what's both? 0.32. What's B? No, B, the probability of B, 0.42. So it's both over just B, all the B, the B. And then that's your answer, whatever that is.
It's a good flip though.
Oh, did I flip them?
Or maybe I'm just wrong. No, like the one. That's the probability. We just have to subtract 35, 32. Oh, yes, I got it.
Okay, I got 0.762. All right. What are we gonna do with the next one? We got all these kids in the gym. They like basketball. They like volleyball. They like soccer.
I got this.
What are we gonna do?
The three circles.
It's gonna be a Venn diagram, and it's gonna have 3 circles. And the circles, there's 100 of them,
Basketball, volleyball.
and basketball is 32, don't put 32 in there yet. Volleyball is 29, and soccer is 53. 2 of them like all 3 sports, so that number we can fill in. 22, like only basketball. 18, like only volleyball. And 40, like only soccer. So at this moment, those are the only numbers that can go in our Venn diagram. We're gonna have to figure out all the rest of them. So who remembers how we did that yesterday?
22 plus A plus B plus
We
B.
gave these letters, so I could call this A and B and C. Then we know that 22 plus B plus 2 plus A has to add up to 32. Which means A plus B has to add up to 8. Should I subtract right? And then B plus 18 plus 2 plus C has to add up to 29. So B plus C is 9. Good? And then A plus 2 plus C plus 40 is 53. So A plus C is 11. So now, somehow, you're gonna solve this.
Substitution elimination.
I like to just take, like if I just put the top and the bottom, these two, and I multiplied this one by a negative and added them together, I would have B minus C equals -3. Is that too much of a stretch for you? Did you get that? I just added these together and got that. But I already know that B plus C is 9. So therefore, 2 B's are 6, and B must be 3. So if B is 3, then A has to be 5. And if B is 3, then C has to be 6. Now I can answer whatever question they ask me, so what do they want to know? I'm gonna pick one at random. What's the probability he likes only volleyball and soccer? Now, volleyball and soccer would be these guys right here, wouldn't it? Because if I try to include that, that would also be basketball. So 6 over 100, 0.06, yep. Now there's 100 kids. So 6 of them, 6 out of 100, that's my probability. Doesn't like any of the sports. I need to figure out how many are out here. Add them all up, subtract from 100. So if I add them all up, let's see. Is it 96?
That's what 93, 96.
I got 96 also. So I think there's 4 kids out there. So the probability I pick one that doesn't like anything is 0.04. All right, biggest serving percentage is 0.815. If she serves 12 times, find the probability that she will make exactly 11 scores. Tell me how I'm gonna do this problem. We've already done some like it today.
It's
What am I gonna start with? Blake?
12 to 11.
12 to 11. Katie is gonna serve 12 times, and I want her to score 11. So 11 out of the 12. Any of those opportunities. So she's doing it 12 times, I'm picking 11 of those to be scores. Now what? That's how I start. Now what? 0.815 to the 11. Because it says her percentage is 0.815. So I want her to do it those 11 times. But there's one more time. What's that number mean? Whatever 1 minus that is, right, so 0.185, I have no idea, double check that.
That's right.
Is that right?
Yeah, that's right.
And that will be the answer to the question. This is exactly like guessing on the test. Right? She serves and what's gonna happen? I'll make it, she's not gonna make it. Just like rolling a die. I'm gonna get what I want, I'm not gonna get what I want. Those problems are all exactly the same.
All set. I guess dominated that paper.
0.234. All right, here we go, we're almost done. All right, here we go. 2 decks of cards on the table. 2 decks of cards on the table. Peter draws 1 card from each pile. Find the probability that both are red. So in other words, A is, you want a red one and a red one.
Would it be, it's not 104, but I think we only have to do
He walks in, he draws a card out of this deck, what's the probability it's red?
Let's do a tree.
52C 13.
Stop. How many cards are there right here?
52.
So it's 26 over 52,
Yep.
which is 1/2.
Yep.
Right, I'm picking 1 card out of the deck, don't make it harder than it is. I'm not dealing a hand, I'm not, no. I'm picking 1 card. There's 52 cards here, 26 of them are red, so my chance of getting a red out of pile 1 is 1/2. What is my chance of getting a red out of pile 2? 1/2. So what is my probability of getting a red and a red? 1/4. If you think about it, I mean, this is the easiest way to do the problem, but if you think about it, if you pick 2 cards, you're either gonna get red, 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 black, black, red, or black, black. So there's really only 4 things that can happen, and you're only interested in the red, red option. So so 1 out of the 4. All right, neither is red.
Same thing.
That means they are both black, which would be exactly the same problem, right? Exactly 1 is red. Well, that means I'm going to get red and black, or I'm going to get black and red. Would you agree with that? Here are my 2 piles. I'm gonna get black, red, or I'm gonna get red, black.
The same again.
It's not the same again. Because this would be 1/2 times 1/2, wouldn't it? Which is 1/4. This would be 1/2 times
And then you
1/2,
add.
which is
like we're doing
1/4, but it could be either one, so
So it's just
you
1/2.
add them. Yeah.
So,
And again, if you think about it, when you choose a card out of each thing, it could be red, 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 black, black, red, black, black. 1 out of the 4 is red, red. 1 out of the 4 is black, black. 2 out of the 4 is 1 of each, right? So 1/2. 1 is black. Oh, this is trick. Oh no, this one's okay.
Yeah, so
1 is black and the other is a diamond. Now, I don't know what's coming out of what pile. So here's pile 1, here's pile 2. I could get black diamond or diamond black. So I need to do both. So black diamond, black and diamond, or diamond and black.
so 1/2 times 1/4.
So black would be 1/2. Diamond would be 1/4.
And then it's
So that's 1/8. Or diamond and black. So what's the answer to the question? 2/8 or 1/4. Neither is an ace. So I'm gonna reach in and grab a card right here, and it can't be an ace. 48 out of 52. Now, I know that reduces, so you can reduce it if you want. 12/13. But that's the idea, right? I want a not ace card. And I want another not ace card. I got 0.852 as a decimal. I could convert that to a fraction to get 144 over 169. 12 squared over 13 squared. Okay, does that make sense to everybody? How about both our aces?
4 out of 52.
4 out of 50, so 1/13 times 1/13, which is 1 over 169. I don't know what decimal that is. The first is a face card. Let's stop right there. Here's my deck of cards. What's the probability I get a face card out of it? 12/52.
Oh,
The first is a face card. I know that reduces, but just leave it over for a minute. And the second is a 6. And 4 52s? Aren't there 4 6s? Now, see how they stipulated the first and the second? So there's none of this or stuff going on. This is the first one, this is the second one, period. And finally, the first is the Queen of Spades, and the second is the 6 of Diamonds. Probability I'll get the Queen of Spades. 1/52. Probability I'll get the 6 of diamonds, 1/52. So it's 1/52 times 1/52. All right, that took a long time, but we got through it. Hopefully we answered whatever worry areas you had. We have office hours tomorrow, but not on Thursday.
So that's all that's on our plate.
Yeah, the question is just probability questions. Just probability questions. All right, let's get our notes out now. And we're gonna start section 9.4. We only have 2 more, 9.4 and 9.5. That's the end. So, yeah, I know, it's
No, I
that day.
didn't.
All of our fours.
I circled the box.
9.4
I did not.
is all about sequences. All right, guys? It's all about sequences. Maybe brand new stuff, so this will be interesting, so Jimmy, we can like pay attention. Some examples of arithmetic sequences. Let me just put a couple on here. 1, 3, 5, 7. That is called an arithmetic sequence. Another example. 15, 12, 9, 6. Another arithmetic sequence. Both of these sequences, I hope, you could continue. In other words, if I said what comes next, you could tell me. Because why? What's going on in these? In both cases, we are adding the same number. We just keep adding the same number. That number that we are adding is called the common difference. The number that we add when we get from term to term is called the common difference. So for this sequence, the common difference is 2. What is it for this one? Not 3, -3. Aren't I adding -3? You can add positives, you can add negatives, you can add whatever you want. But if you're arithmetic, you must be adding the same number over and over and over again. That's how you know if something's arithmetic. The formula for an arithmetic sequence is this. You do not need to, we're going to get several formulas. You do not need to memorize the formulas. However, all I'm giving you are the formulas. So you need to understand what's what. Because you're going to be plugging numbers in here to figure that out. Okay? So we'll talk about that more when we get to an actual problem. Now we need to talk about geometric. All right, here's an example of a geometric sequence. Here's an example of another one. What's a geometric sequence? In order to get from term to term, we are multiplying by the same number. So, and that same number is called the common ratio. So for this sequence, the ratio is 3. And for this sequence, the ratio is 1/2. Right? And your formula for a geometric sequence is this. Now you will notice that some of the letters are common. They mean the same thing. You'll also notice that your arithmetic formula has a D in it. And what do you think that D stands for?
Different.
The difference? Your geometric sequence formula has an R in it, and that stands for your common ratio. All right, let's do a problem. Consider the following sequences. Tell what type they are, give an explicit formula, and give a recursive formula. Well, this is a lot. Let's start with the first part. What type is A? Arithmetic. With a common difference of 4. You are to write an explicit formula. These are explicit formulas. In a minute I will explain that after I get one written. But we're going to use this right here because it's arithmetic, and we're going to write a formula. A sub n equals 3 plus 4 times n minus 1. That's the beginning of my formula. I have to simplify it. But what do you think A sub 1 stands for? Look what I plugged. Oh, wait. I was using the wrong formula. I'm sorry. I'm doing the wrong thing. This is, oh no, I'm using the sequence on the table. I'm right. Sorry about that. I'm all confused. I'm right. I'm using this sequence right here. So what do you think A sub 1 stands for? The first term. This means, this is notation, sequence notation for the first term. And it is read A sub 1. So in this sequence, if for some reason I wanted A sub 2, A sub 2 would be 7. A sub 3, A sub 4, and so on. So what does A sub n stand for? The nth term, right? Some term. So if n is 10, it would be A sub 10. But I don't know what n is. So I'm not filling in any numbers there. The only thing I know in my formula is the first term is 3 and the common difference is 4. So I'm going to simplify that by distributing and collecting like terms. So if I did that part right, that's what I end up with. So this would be what's called my explicit formula. Now why is it called an explicit formula? Because if you're doing a problem, and there are practical applications of this, if you're doing a problem and for some reason you've got this sequence of numbers, you can see what's going on, but you need the 1000th term. You do not want to write out all those to the 1000. You can just plug in 1000, and the 1000th term would be 3,999. 4,000 minus 1. An explicit formula gives you whatever term you want. If you wanted the millionth term, you could get it. That's what an explicit formula does. And it comes straight from the original. Plug in your first term, plug in your common difference, and you've got it. Now that is different than a recursive formula. A recursive formula says, how do I get the very next term? So if you look at the sequence they gave you, what would you tell me the next term is? 19, thank you. And how did you get 19? Added 4. So you took that one right there. You took some term and added 4 to it. You took some term, in that case, it happened to be the 4th term, any term, and you added 4 to it. And that gave you the next term in the line. Do not be frightened by that notation. If n is 8, if n is 8, what's n plus 1? 9. So if you take the 8th term and add 4, won't you get the 9th term? If you take the 12th term and add 4, you will get the 13th term. This is called a recursive formula. Now, there's another piece to this that I gotta add in real quick. A recursive formula won't work unless you know where to start. You have to know, okay, I'm gonna start with 3. And after that, I'm just gonna keep on adding 4. If this is all you have no idea. Because you know you have to add 4, but you don't have anything to add 4 to. So in a recursive formula, when you're writing one, there's 2 pieces. There's the pattern, add 4, and then there's the starting point you have to leave. Alright, I'm gonna stop there because we're gonna have time to do the next one. So next time, we'll have a little quiz, and then we will continue on with our conversation about sequences. Early on in the year, we talked about linear functions. Arithmetic sequences are linear, and we talked about exponential functions, geometric sequences are exponential. Just in case you were wondering if there was any connection to anything. I do, because I have 2-sided paper, and
I think that you just knew that he wouldn't notice.
because he wanted to do it.
Why are you gonna do it? Never seen
I'll
my
see if I have another one, Charlie.
Howard, this next group, please.
Yeah, have a good day.
No, I'm leaving.
Have a great day.
Yeah, we got to, me, Chase, and Meek, and Coors, I'd like to set up the yard. They're not yard, whatever the shit. The hill?
Did you bring a resource next?
Okay, Charlie.
I've waited. Wait, we did for you to do that?
Yeah.
I always use
I'm gonna come, I'm gonna wait.
but if it's two-sided and I don't realize it. Sorry about that.
That's fine.
I'm in there scrounging around in the recycle bin, and sometimes I grab a stack, and I don't look at it quickly enough.